Okay, and we are live on YouTube. Okay, guys, welcome to Keen and Can Do Introduction to Learning C Programming, Episode 9. Sorry, it's been about a week since my last stream. It was just busy. So, we're going to begin with Chapter 12 after I get a few things out of the way. That being that I am streaming these websites and these books on a Creative Commons version 4 share alike license and version 3 attribution license. So with that, let's all learn together and continue with chapter 4. If we look at the where we left off, we had this Charmander, I think, here, which was doing a, let's go to projects, we'll go to C, chapter 10, Charmander, there we go. Okay, so yeah, this was taken in a, char, I'm calling that C, and then putting a new line, and then printing out the ASCII value, and then printing out put char, so putting out the actual char value using the put char, and then using put char again and printing out 33, which is the ASCII value for a particular value that we wanted to get there. Actually, I think we could change this and do just C, right? It should operate the same. So let's save this. Let's compile, because put char, if I remember correctly, and then we'll go, remember we were just running it from like command prompt here. And then if we go down here, we'll see that oh, let's do the list. Okay, we'll just do Charmander, and then let's say we're gonna do 7, and then yeah, 7 char input was 7. Yeah. Okay, so ASCII value was 56. And then char input was 7, and then it prints it again. Okay. And then if we did it again with space, it should be 32. Cool. And if we did it again, what is that? Exclamation point is 33? Yeah, exclamation point was 33. So char ASCII value is 33%, %D. Then printf char inputted was ASCII value. And then why did it print it again? Char inputted was. Put char. Oh, and then it puts it again. I'm kind of confused now why we had the... Is my sound working today? Hopefully it is working today. I think it probably is. I'm kind of confused why it did. I understand ASCII value 33, and then it immediately prints... Okay, the char entered in. Then why does it immediately print the char again? Is that because print char, the info, SDIO, and we'll do put char. Int put char. Yeah. Oh, so it puts it. So my question about all of this is, why does it... Let's do... Oops. Compile. Let's do GCC minus G3. Oh. Render. PDB. Okay. Um, and we want a breakpoint. Breakpoint. Where do we put a breakpoint? Oh, okay. B. B8. Run. I need to go back to the real quick. Let's just go back to compiling and debugging. Debugger. Breakpoint main run. Oh yeah, display. Display C equals 33. Next. Next. Breakpoint, jump finish. So if I wanted to, prevent it from %C. Oh, I see now. I think I know. I think it's because let's do 4. Okay, char inputted. Do functions get evaluated? Because it evaluates, yeah, substitution, it evaluates put char, which outputs, and then puts it again. So what if we go and we go back here? Yes. Yes, because you don't need, because just having to put the char there is enough to, Okay. Okay, that's cool. Just a little quick catch up there. We're in statements and control structures. Chapter 12. The bodies of C functions, including main functions, are made up of statements. These can either be simple statements that do not contain other statements, or compound statements that have other statements inside them. Control structures are compound statements like if, then, else, while, for, and do, while, that control how or whether their component statements are executed. Simple statements. The simplest kind of statements in C is an expression followed by a semicolon, the terminator for all simple statements. Its value is computed and discarded. Examples: x equals 2, an assignment statement; x equals 2 plus 3, another assignment statement; 2 plus 3 has no effect, will be discarded by smart compilers. Puts high, a statement containing a functional call; root 2 equals square root 2, an assignment statement with a function call. Most statements in a typical C program are simple statements of this form. Other examples of simple statements are the jump statements: return, break, continue, and go to. Go to. You're never supposed to go to. A return statement specifies the return value for a function if there is one, and when executed it causes the function to exit immediately. The break and continue statements jump immediately to the end of a loop or switch, see below, or the next iteration of a loop. We'll talk about these more when we talk about loops. The goto statement jumps to another location in the same function and exists for the rare occasions when it is needed. Using it in most circumstances is a sin. Do not pass go. Do not collect $200. Do not use goto. Compound statements. Compound statements come in two varieties: conditionals and loops, which we'll explore in depth in the next sections. Conditionals. There are compound statements that test some condition and execute one or another block depending on the outcome of the condition. The simplest is the if statement. If house is on fire, ouch, scream, run away. The body of the if statement is executed only if the expression in parentheses at the top evaluates to true, which in C means any value that is not 0. The braces are not strictly required and are used only to group one or more statements into a single statement. If there is only one statement in a body, the braces can be omitted. So that's interesting that every value besides 0 is a truthy value. Except 0. So that would mean we'd have to be careful. Because you could put like an assignment statement inside instead of a conditional comparison. Interesting. The braces, okay, if programmer is lazy, omit braces. This style is recommended only for very simple bodies. Omitting the braces makes it harder to add more statements later without errors. If under attack, launch counterattack. Executed only when attacked. Hide and bunker. Do not indent like this. Executed always. In the example above, the lack of braces means that the hide and bunker statement is not part of the if statement. Despite the misleading indentation, this sort of thing is why I generally always put in braces in an end. Always put end braces. This sort of thing is why I always put braces, an if statement in braces, I guess that should be written as. An if statement may have an else clause whose body is executed if the test is false, i.e. equal to 0. If happy, call smile. Else, call frown. A common idiom is to have a chain of if and else if branches that test several conditions. If temperature is less than 0, puts brr. Else if temperature is less than 100, puts hooray. Else puts ouch. This can be inefficient if there are a lot of cases, since the tests are applied sequentially. For the test of the form something double equals something, the switch statement may provide a faster alternative. Here's a typical switch statement. Print plural of cow, maybe using the opposite dual number construction. Switch, number of cows. Case 1, puts cow, break. Case 2, puts cowin, break. Default, puts cows. This prints the string cow if there's one cow, cowin if there are two cowin, and cows if there are any number of cows. The switch statement evaluates its argument and jumps to the matching case label, or to the default label if none of the cases match. Cases must be constant integer values. Does the cases always have to be integer values? Here it's just, is it always, there's a C statement, I'll have to look that up. The break statement inside the block jump to the end of the block. Without them, executing the switch with number of cows equal to 1 would print all 3 lines. This can be useful in some circumstances where the same code should be used for more than one case. The break statements inside the block jump to the end of the block without them, executing the switch. Break statements inside the block jump to the end of the block. Without them, executing the switch with number of cows equal to 1 would print all 3 lines. This can be useful in some circumstances where the same code should be used for more than one case. Switch C, case AEIOU, type equals val, break. Default type equals constant, break. Yeah, I like that. I like that's called fall through casing. We don't have that in C sharp, I don't believe. I could be wrong. Pretty sure we don't have it though. Or when a case falls through to the next. Yeah. Switch, countdown start. Case 3 puts 3, case 2 puts 2, case 1 puts 1, case 0 puts kablooey, break. Default puts I can't count that high, break. Note that it is customary to include a break on the last case even though it has no effect. This avoids problems later if a new case is added. It is also customary to include a default case even if the other cases supposedly exhaust all the possible values, as a check against bad or unanticipated inputs. Switch, olive size. Case, jumbo, eat olives slowly. Break, case, colossal, eat olives quickly. Break, case, super colossal, eat olives absurdly. Break, default, unknown size, abort. Break. Though switch statements are better than deeply nested if constructions, it is often even better to organize the different cases as data rather than code. We'll see examples of this when we talk about function pointers. Nothing in the C standard prevents the case labels from being buried inside other compound statements. One rather hideous application of this fact is Duff's device. What is Duff's device? Let's play with some switch statements first, and then we'll do Dutch device. So we need to create a directory. We'll call it chapter 12 because that's where we are. We'll find a file in chapter 12. And let's call it test.c because that's what we're doing. Include standard input at h. Oops, I have to include it though. Ooh, h. And then let's see, int main void return 0. Okay. What do we want to do here? Let's get a char. Let's get a char and tell them if they entered a letter. No, let's just do, let's just do int c equals get char. Which the, let's say case is C is less than 90. Print f %c is a small char. Then we'll do C. Okay, and then break. Case C is less than 100. Print f %c is a medium char. I don't know. Then we'll break. Let's do default. And then we'll say puts. I don't know what to do with that char. Okay. Okay. And then we can save it, and then we'll compile it. Let's make, we'll call it test. Alright, and then we gotta run it. We gotta do that over here though. Let's cd back and then chapter 12. And then let's call it test. Wait a second. Did I not save it? Case label does not reduce to an integer constant. So you're not allowed to do that then, maybe. Oh. We didn't close the case. That way? No, it's not. Okay. Expected a token before break. Okay. I don't understand why it's saying it doesn't reduce to a constant, though. Label does not reduce to an integer constant. Let's look up the case. Let's ask ChatGPT and see which statements can you not use intervals. Oh, okay. So in that sense, we would have to use... See, we're learning. In that sense, we'd have to use for this... Okay, so we have to do C equals... Which do case? Case 33. Case... Case 95, is it 95? Okay. Now we can compile it. That's something we'll have to remember. Main T? There's no main T around here. There we go. Now, test. Let's do A. Okay. Do A. What is 95? Oh my god. Let's do this one. Blank is a small char. Oh, what is 95? I thought A was 95. Let's do Charmander. Tell us. After 10. Charmander. A. 65. Oh. So I need 30 letters. We only have 26. Oh, great. Z? So what is Z? 90. Oh my god. Okay. What is this? 58. Okay, what is this? 59. Oh man. What is this? 32. What is... Oops. 7. 55. What is backspace? 10. What is shift? 10. Okay. I need an ASCII table. Do I have an ASCII table here? ASCII. Boom. Where is the ASCII table? Table. ASCII. Oh. Small a? Oh, I didn't realize that. It's small a. 97. Oh, I want 95. Oh. Oh. Do an ASCII table. Do I not have an ASCII table anywhere? No. $95. The underscore? It is the underscore. Okay. So let's do test and underscore. Command not found. What? Underscore. Blink is a medium char. Yeah. Okay. And then if I wanted to, after that, then we could just do puts. And we'll do our escape character file again. It's fun playing around with C. It's really simple. You can do a lot of stuff. Look at that. Blank is a medium char. 33. Blank is a small char. I don't know what to do with that char. Cool. Okay. I want to save this. Evernote web clipper. Clip image. Okay. Now I have soon I'll have a thing there. There it is. Now I have an ASCII table. Okay. So switch statements are better than deeply nested if constructions. Yeah, we're going to go back to now looking at the switch statements. Or back to the text now. Though switch statements are better than deeply nested if constructions, it is often even better to organize different cases as data rather than code. We'll see examples of this when we talk about functional pointers. Note in C standard prevents the case labels from being buried inside other compound. Nothing in the C standard prevents the case labels from being buried inside other compound statements. One rather hideous application of this fact is Duff's device. Okay, let's look up Duff's device. In the C programming language, Duff's device is a way of manually implementing loop unrolling by interleaving two syntactic constructs of C, the do-while loop and a switch statement. Its discovery is credited to Tom Duff in November 1983, when Duff was working for Lucasfilm used it to speed up a real-time animation program. Loop unrolling attempts to reduce the overhead of conditional branching needed to check whether a loop is done. By executing a batch of loop bodies per iteration to handle cases where the number of iterations is not divisible by the unrolled loop increments, a common technique among assembly language programmers is to jump directly into the middle of the unrolled loop body to handle the remainder. Duff implemented this technique in C by using case label fall through feature to jump into the unrolled body. Original version. Duff's problem was to copy 16-bit unsigned integers, shorts in most C implementations, from an array into a memory-mapped output register denoted in C by a pointer. His original code in C looked as follows. Send to from count, register short, to from register count to. Well, this code assumes that initial count is greater than 0 since the output location. Okay, we're gonna look that up later. My speaker's okay? You didn't join? You didn't join? Okay. I don't think any. How many? Zero. Zero streamers. Warning, the stream's current bitrate 26 is lower than recommended. We recommend that you use a stream bitrate of 60. Well, how do I do that? I'm not the one that took the bitrate down. Is it because my brother's playing video games? Yeah, I have 640 megabits. Is it OBS? Whoop. My son just knocked down the thing there. Okay, I'll have to look later. Hmm?
Do you smell it? Do you smell it?
No. Did you smell?
It's a couple. It's just a...
Alright. Let me finish the stream and then.
When he gets up, it's gonna smell.
There are three kinds of loops. Go up loops now. There are three kinds of loops in C. The while loop. A while loop tests if a condition is true. If so, executes its body. It then tests the condition is true again and it keeps executing the body as long as it is. Here's a program that deletes every occurrence of the letter E from its input. Include standard input while C get char is not equal to end of file. Switch C case E or case E break default put char C break return. Note that the expression inside the while argument both assigns the return value of get char to C and tests to see if it is equal to end of file, which is returned when no more input characters are available. This is very common idiom in C. Note also that even though C holds a single character, it is declared as an int. The reason is that end of file, a constant defined in standard input-output H, is outside the normal character range, and if you assign it to a variable of type char, it will be quietly truncated into something else. Because C doesn't provide any sort of exception mechanism for signaling unusual outcomes of function calls, designers of library functions often have to resort to extending the output of a function to include an extra value or to signal failure. We'll see this a lot when the null pointer shows up in the chapter on pointers. So let's look at that again. So we have while the C equals get char, So when you wrap that up like that, does that... Yeah. Is not equal to end of file. Which C. Do while loop. The do while statement is like the while statement, except the test is done at the end of the loop instead of the beginning. This means that the body of the loop is always executed at least once. Here's a loop that does a random walk until it gets back to 0, if ever. If we change the do while loop to a while loop, it would never take the first step because pause starts at 0. Int pause, position of random walk, s random time, initialize random number generator, times 0, do pause plus equal random, and hexadecimal 1. Plus equal random and there's a random walk until it gets back to 0, if ever. Pause equals 0. Pause plus equal random and that's not the same and though, isn't that the... What is that? Is that a sad ghost? Can you hear me or no? I didn't even know you could do emojis. Okay. So this is isn't that the programming? Oh, that's all the emojis. Every emoji. Is this the... I can't remember if that is the... It's one of the... Okay, chapter 12. It's one of the... logical bitwise operators. Yeah. That's the logical bitwise operator. Yeah, that is crazy. I didn't realize there was all those. The bitwise blank, bitwise negation, bitwise and X and Y. Oh, okay, so if we remember that again from last time, I think that... Did we have... Oops. Did we have org files? Didn't I have org? Bitwise org.org. Yeah. Whoops. Yeah. Okay, so the way that works is we have 1 and 1. Yeah, true and true, yes. So they both, right? True and false is false. False and true is true. And false and false. And false is true. So having that in mind, we go back to chapter 12. We have is that the one where you strip? Because this would be hexadecimal. I still don't understand why you have to. Yeah. Let's try this. Let's say, okay, so they're having random. I don't even know what random generates though. Is it just random from 0 to 1? You know what? Let's look it up. We do have documentation. So let's say we're in info time. Info time. Okay. Info time.h. Man time. Great. Man 3 time. No, this. Man. Oh, program. Library calls. Yeah, man. Wait. Oh. Man 3 time. No, that's not. No, it's a function for God. Oh, we don't have manual entries for that? Well, I didn't realize that. Where? Oh, the time is in that. Okay. Oh, standard lib is random. Long int random. The random function is nonlinear. Little random numbers in a range from 0 to rand max. Very large. Where's random max? What's random max? Let's see that. Let's write a little program. Write a little program for me. Write a little program for me. Well, I'm already writing a program here. Okay. Oh, we'll write another one. Write another one. What's max? What's max.c? Okay. Include standard page. Include okay, int main void return 0. Okay, let's say do I not? What is it called? Random max? Rand max, okay. What's the size? Long int. Long int. Extern. Long int. Max rand. No. No, I have to actually name it. Rand max. Rand max. Print f the max random number is sent L. I'll make max. Nothing to be done. Oh. Is it LD? Format specifiers. Oh, we have them right here. Oh, okay. Yeah. Log it. Just trying to find where to find that. Oh. Long int. So back to my didn't we loading point variables, yeah. Scope and extent. Turn Which can we say? Which random? Find random? Apropos random? Locate a command. Okay. Where is random? Oh, yeah. Man 3. That's just the man files. Apropos SDI lib. Where is find? Oh. LS bin bin grep the header file. Oh, sweet. GCC minus H. Very nice. Very nice. Okay, so let's do that. File. GCC minus H. Oh, okay. User include. Okay. User include. Grep. Okay. define rand max. Okay, so does that mean when you do a definition like that? So we didn't do defines yet. No, we didn't. Is that in like here? No. Oh. Where's defines then? Okay, I'm pretty much done. Fine. Okay. So back to where we are today. The do-while loop is used much less often in practice than a while loop. It is theoretically possible to convert a do-while loop to a while loop by making an extra copy of the body in front of the loop, but this is not recommended since it's almost always a bad idea to duplicate code. That is true. Okay, this is a good place to stop for tonight. I kind of went off on a tangent here, attempting to get, I'm not sure why, rand max. What was the reason for my compilation failure? Oops. included from. So this is int. That doesn't. Expected identifier. Okay, so personal name. Yeah. Extern. Can a clue guards your header prevent multiple inclusion process. Okay, so wait a second. So I didn't even need to have it as an extern? What? Oh. I don't even need to have it at all. Because it's define macro and I can use it inside. Man. Okay, we get this working and we're good to go. Yeah, okay. So it's gonna print it out now. What's max? Yeah, there it is. Oh man, and it's an int, not a long int. Why did it say it was a long int? Long int. It's long? I don't know. It's not short int? Okay. I'm gonna have to get better on those. Okay. Cool. Well, at least we figured it out. That was fun. All right then, guys. Thank you for watching today. We'll try to be a little bit more on top of it with the streams for the rest of this week. I hope you got something from it. If you like this kind of thing, leave a comment below. Hit that like button and subscribe. We'll catch you later in Keen and Can Do. Bye-bye.